and then hybridization, where we are very specific, and we talked about the sp2 hybridization. We also had someone who wanted to share with us something else that we looked at. Let's put up the hand, and then we can move on to what you want to share today. Any other person to share with us what we looked at last time? Okay. So if you don't forget also, okay, I can see Nyirimbibi. Nyirimbibi, you can tell us.
Okay, well, it's Nyirimbibi. We also looked at isomerism of alkenes and also the conditions.
And also?
The conditions.
The conditions for?
Alkenes.
Conditions?
Yes, where we looked at the presence of a carbon-carbon double bond.
Okay. Okay, I guess so. We looked also at
and also the types of isomerism.
And also the types of isomerism. Okay, thank you very much. So that is nice. And we said now today we shall be looking at specifically at the chemical properties. You can mute now, Ruth. You can mute. Thank you. So today we are going to look at majorly the chemical properties of alkenes, and then at the end of this lesson, we shall also be able to have one scenario item, which we shall be going through, applying all the work that we studied in the previous lesson and what we're going to be looking at in this lesson. And as I said, if we have any inquiry, any issue, let's keep on using the chat section, and also we keep on raising up our hands. So chemical properties of alkenes. Let me have one person to read for us those 2 points by show of hands. Who can take us through the first 2 points? Okay. Yes, Jovia. Okay, Jovia Sala, you can unmute. Jovia Sala. Jovia Sala, you unmute. Jovia Sala. Okay. Baswari, you can unmute.
Sir, good afternoon.
Good afternoon, teacher.
Okay, let me have Sarah first.
Good afternoon, teacher.
Sarah, you can take us through then.
So the chemical properties of alkenes.
Okay.
The first one, alkenes are highly reactive hydrocarbons than the alkenes, and their functional group is a carbon-to-carbon double bond. Then the double bond consists of one sigma bond, which is strong, and one pi bond, which is weak and easily broken.
Okay. Now, there is one point. You keep your microphone on. You have read for us that alkenes are high reactive hydrocarbons than alkenes. Why do you think alkenes are more reactive than alkenes? This statement. Sarah, you can take us through that. Why do you think they are highly reactive?
I think they're highly reactive due to the strong sigma bond between the carbon-to-carbon double bond.
So they are more reactive because of the strong sigma bond?
Yes, that's what I think.
Okay. Okay, thank you. Let's have also Shadia. Shadia? Okay, Shadia. You can unmute.
Excuse me, sir.
Yes.
I think they are very reactive just because they are saturated and they have that pi bond, so they are able to react.
They are
They are unsaturated,
unsaturated.
so that is why they are very reactive.
Okay. So what makes them more reactive is because of the unsaturation.
Yes, sir.
Okay. Thank you. So we are saying that what is making them more reactive? Is it because of only the unsaturation? Okay. So you're telling us yes, no. Okay. Let's also see someone else who can share with us. Thank you. Let me have Gilbert. Yes, Gilbert.
I think the alkenes are more reactive than alkanes because when you look at the alkenes, they have a double bond. So that double bond is made up of two bonds. One is sigma, another one is a pi bond. So the pi bond is, we know that the pi bond is weaker than the sigma bond. So during the reaction, it is very easy to break up the pi bond found in the alkenes, hence making them so reactive because that pi bond, it has what you call the pi electrons. So these pi electrons are highly, they can be easily used, or they can easily attack the electron deficient species, making the reactive to be easier than the one in the alkanes.
Gilbert, your name is Gilbert.
Yes, sir.
Okay, thank you very much. I think that was a very good explanation, and is telling us that it's because of the double bond, and is continuing to tell us that this double bond, it consists of two bonds, where one is a sigma bond, and then the other one is a pi bond. The sigma bond, very strong, and has told us that the pi bond, it is weak, and therefore it can easily be blocking. So these pi electrons are the ones which are responsible for the high reactivity. That's why in the NB, we can see that we are saying that the pi bond is responsible for the high reactivity of alkenes, especially the addition reactions. So there are another point that the pi electrons are therefore attacked by electron deficient species, and for this reason they undergo electrophilic addition reactions. So those are the two key points that we could be able to see under the chemical properties of alkenes. Then we have seen that they are very reactive, and what makes them more reactive is because of the presence of the double bond, which consists of the two bonds, the sigma and the pi bond. Okay, there's someone who has a hand up. Yeah, I would like us to move to the next part, but after hearing from Anita. Anita, what are you saying? Okay, Anita's hand is now down. It's all right. So we can now move on. I would like to ask one question. Which name is given to electron deficient species? Electron deficient species. Anita's hand is up. Yes, Anita? Anita, you can unmute.
Excuse me, sir.
Yes, please.
I would like you to explain me more about the pi electrons and therefore attacked by electron deficient species. That part I've not understood very well.
Okay. So you would like to know more about pi electrons?
Yeah.
Okay, you keep on mic. So Anita, when you talk about pi electrons, last time in our first lesson, we looked at hybridization. And through the hybridization, which we say that for these alkenes, they undergo what we call the sp2 hybridization. And it is through this hybridization that we're able to see that the sigma bond and the pi bond form between the carbon to carbon atoms of alkenes. So the pi bond and the sigma bond, the pi bond is very strong compared to the pi bond. And you recall each bond is made up of a pair of electrons. So when you talk about a sigma bond, that is a pair of electrons. And when you talk about a pi bond, that is another pair of electrons. So we are saying that this pi bond is the one which is responsible for the high reactivity of alkenes. Why? Because it is weak and therefore it can easily be broken. So during the reaction, the pi electrons are the ones which are attacked by electron deficient because they can easily be broken and therefore they are exposed. Therefore, they can easily be attacked by the electron deficient, the species or substances which are yearning for electrons. We are going to look at that as we go to our next lesson. As we go to our next slide, we shall be able to look at those species which we call the electron deficient and those ones which are electron rich. And I've seen in our chat, someone is telling us electrophiles and then another one telling us the nucleophiles. So in our next slide, we shall be able to see the electrophiles and what the nucleophiles are. Anita, are we okay there?
So, sir, the pi bond is the one that is related to saturation, eh?
So you're saying, is the pi bond the one related to saturation?
Yeah, of the alkenes being saturated because of the double bond that they are possessing, that they can be easily broken down, eh?
No, for alkenes, they are saturated, while for alkenes, for them, they are unsaturated. They are unsaturated. For them, they have some free electrons present. Those ones the ones which form the pi bond. That bond is the one which is responsible for the unsaturation in alkenes. Are we there?
Okay.
Then when you go when you go to alkynes, for them they have 2 pi bonds, which means alkynes then become even more reactive because they have 2 bonds which are having pi electrons that are also weak. Therefore, they can also easily be broken. So the pi bond, the pi electrons are the ones responsible for the unsaturation in the alkene and also in the alkyne.
Okay, got it. Thank you.
Okay, someone is asking, what about the hybridization we talked about? We couldn't go to hybridization before we finish alkenes, and therefore we shall be able to see by the end of this session, we have said in our next lesson shall be tackling only hybridization plus also scenario items in regards to what we have covered in the alkenes and also in other topics. Okay, thank you. Unless we have any other question, we can be able to move on. If you have any question, please keep on putting in the chat or you raise up the hand. So we are coming to, we have seen that in that point number 2, that the pi electrons are therefore attacked by electron deficient species, and for this reason, they undergo electrophilic addition reaction. And here is that question. What is an electrophilic addition reaction? Jovix, thank you. Jovix saying electron deficient is also called electrophile. Thank you very much. We shall be able to see all those examples of electrophiles and nucleophiles. Who can first tell us, what do you understand by that? An electrophilic addition reaction, because we are saying that alkenes, they undergo this kind of reaction. And before you go through it, we need to first understand what is electrophilic addition reaction. I'm seeing Daniela. Daniela, you can unmute. Daniela, yes.
Good afternoon, sir.
Good afternoon.
Well, an electrophilic addition reaction is that reaction in which an electrophile adds to an alkene or alkyne to form a single product.
To form a single product. You have said where an electrophile
or electrophilic reagent adds to alkene or alkyne to form a single product.
Okay, thank you. So you're saying that we are adding an electrophile to an alkene to form a single product. What is the property of the product which is formed? What is special about that product that is formed?
I think it should be saturated.
Very good. It is saturated. Very good. That is good. So, which means we are having an electrophile adding up to an alkyne. An alkyne is unsaturated, and then the final product is now becoming saturated. Thank you. Thank you. Daniela, thank you for that submission. Jovix, you have your hand up. You can tell us. Yes, Jovix.
I think an electrophilic addition reaction is a reaction in which an electrophile adds itself across a multiple bond of alkenes or alkynes to form a single product with no loss of any atom.
Very good. You have also added another word, with no loss of any atom. So in electrophilic addition reaction, we don't see any loss of any atom or of any molecule. Thank you. You can keep your microphone on and read for us this one. Read for us.
An electrophilic addition reaction is that reaction in which an unsaturated organic compounds, such as alkenes or alkynes, combines with an electron deficient species, in brackets electrophiles, to form a single product which is saturated.
Which is saturated. Which is almost the same as the one you have given us, only that you have added for us another key point or key one, that during electrophilic addition reaction, there is no loss of any atom or molecule. Thank you very much. Now, let us look at the list. They are saying, can you list some examples of electrophiles? Examples of electrophiles and examples of nucleophile, and also understand what nucleophiles are. From this definition, we have seen that electrophile can be electron deficient species. Electron deficient species. But now, what is a nucleophile? Do you have a hint on what a nucleophile is? Yes? Okay. Okay, we can have another person. Teddy. Yes, Teddy. Yes, Teddy.
A nucleophile is an electron deficient species.
It is what?
A nucleophile is an electron deficient species.
Hi, your network is not clear. If you can change your location, or you speak again. Yes. Okay, someone saying electron rich species. Okay, good. Electron rich species. Okay, then we have seen electrophile. is electron deficient. And someone in the chat was telling us what deficient means, lack. So which means for these ones, they lack electron, they are deficient. When we talk about someone is deficient of maybe a particular nutrient, which means he lacks that particular nutrient. So they are electron deficient species, while nucleophile, for them, they are electron rich species. Okay. We have Daniela, you still have the hand up. You can unmute. Daniela?
Yes, teacher.
Yes, please.
No, it's okay.
It's okay? Okay,
Please.
now keep your microphone on and then read for us what is down here. You give us an example of an electrophile.
Okay. An electrophile, these are positively charged atoms which attach the region of high electron density, or they are electron deficient species and are said to be electron loving.
They are said to be electron loving. Okay, so I believe in this definition we have added a few key ones. Number one, we are saying that electrophile, they are positively charged atoms. And they are saying that they attach to the region of high electron density, which means they are positively charged and they move towards where electrons are. They attach to the region of high electron density. Or in other words, we can say they are electron deficient species. Species which lack substances, or species which lack electron. And they are adding a one, they can also be said to be electron loving. They are electron loving, therefore they move towards where the electrons are. Can we have some examples? Number one is what? Daniela, you still there?
Yes.
Number one.
Yeah, I'm not very sure, but is it a sulfite? Okay.
You recall,
sure.
You recall we are saying that they are positively charged atoms. Okay, we can give another person a chance. I'm seeing in the chat people are putting a number of them. That is good. Let me have Samsung S. Samsung you have put down. Teddy. Yes, Teddy. Teddy. Okay, Jovia, sir. Teddy, you are there.
Sir, I'm not very sure, but I think it's one of the electrophiles.
Like which one?
Zinc.
He's saying zinc. Okay. We are saying that the positively charged atoms which attach the region of high electron density. Who is that one who was telling us? Sarah, are you the one? Okay, we can have, some of them we have like hydrogen ion, which is positively charged, and therefore it moves towards the high electron density, or the area which has electrons. Number two, we can have ammonium ion. We have ammonium ion. Good. Robert, thank you. That is good. We can have someone is telling us nitrous ion, which is having also a positive charge, and also plus others which may have a positive charge. Someone is also putting for us hydrozomium ion. So those ones, what we are saying that electrophile can be those species which are positively charged and they attach the region of high electron density. Then we can also talk about nucleophiles. Who can read for us? Nucleophiles. What are nucleophiles? By show of hands. very fast to read for us this statement we have. Okay. Okay. Shalom Kadu. Shalom Kadu. Okay, good.
A nucleophile is an atom or group of atoms with negative charges or lone pairs of electrons which attack the region of low electron density. They are said to be electron-rich or nucleus-loving species.
Can you give us examples of such species?
Can ammonia work?
Ammonia. Ammonia, it has some lone pair of electrons. You recall here they say a group of atoms with negative charges or lone pairs of electrons. So even ammonia works. Do you think
water.
Can give us water? Good, with some lone pairs of electrons. Juliet, that is nice. Juliet also is giving us hydroxide ion. Okay. Yeah, that is nice. Many people are giving us a number of them. Someone has also put chloride ion, and also you can say ETC and more others. So those ones which are having a negative charge or lone pairs of electrons which attack the region of low electron density. So this was very important for us to know, so that at the end of it all, when you're doing the mechanisms, because today we're going to look at the mechanisms as we look at these chemical properties. So as we're looking at these mechanisms, we are able to understand where the arrow is supposed to go, from what going to what. You can read for us this statement before you go off. Read for us that NB. Read for us the NB.
In reaction mechanism, arrows move from nucleophiles to electrophiles.
Arrows move from nucleophiles to electrophiles.
Electrophiles.
I think that one is very clear. We are moving from nucleophile, where it is electron rich, to electrophile, where it is electron what? Here it is electron what? Rich. Are we there? While this one is electron deficient. Are you seeing that? So when we talk about the reaction electrophilic, someone is asking, Master, when are we doing synthesis? Don't worry about synthesis. If we study the chemical reactions very well, we are already doing the synthesis. At the end of it all, we can be able to synthesize different substances from different products, from different compounds, from different organic substances. But as we keep on moving, we shall be able to learn all of that. Now, let's move faster. Teddy, you have a question. Let me work on your question and then you can move on. Yes, Teddy? I want us to go straight to chemical reactions now. Teddy, you have a question?
No, sir. My question was about synthesis.
Oh, okay. I believe I've been able to respond to you. So we're going to start with, let's first list all these, the chemical reactions. Teacher, I pray that I finally understand the mechanism. Okay, and Makonikovs, don't worry. I can see Anita and some other person here, they are worried about the mechanisms and reactions. Today is your day to understand all these mechanisms and chemical reactions for alkenes. And the reason why we have gone through understanding what electrophiles are, what nucleophiles are, is for us to understand where is the arrow coming from, where is the arrow going, so that when we begin these mechanisms, it is not just coming from nowhere, but now we understand why the arrow is coming from this substance going to the other substance. Now, chemical reactions of alkenes. We are going to look at around 1, 2, 3, 4, 5, around 6 reactions We have from A up to F. And number 1, we shall be looking at addition of hydrogen. That is, you recall, we are looking at electrophilic addition reactions, where we are adding electrophiles to alkenes to form saturated compounds. And we shall be able to do the equation plus the mechanism for different reactions. What I want you to do is to make sure that you open up your eyes very well and also have where you're noting down that at the end of it all, after this session, there's no question about alkenes that should fail you. That's why I've prepared also a scenario item about the same that you can be able to take it and you try it out as we move from here. We shall be able to get this document after here. Let's not get worried about anything. Okay, let's move faster. Anita, don't cry about polymerization. It is coming. So addition of hydrogen is also known as hydrogenation. That will be our number 1. Then number 2, we shall look at halogenation, from the word a halogen. So when you say halogenation, there we are adding a halogen. Halogens, we have examples of halogen like chlorine, we have chlorine, we have bromine, we have iodine. All of these are halogens. So we shall be looking at addition of halogen, or what we call halogenation, in the presence of inert solvent and in the presence of water. Someone is asking, what about oxidation? Don't worry. It is on number E. This is also known as oxidation. Then number 3, we shall also look at addition of hydrogen halide, what we call the halogenic acid. That will be another part where we shall be adding the halogenic acids or hydrogen halides. Then number 4, we shall be looking at hydration of alkenes. Hydration is addition of water, but this is acidified water. This is the acidified water. Then E, we shall also look at reaction with potassium permanganate, also known as hydroxylation reaction, also known as, which is one of the oxidation reaction. Then we shall also look at the polymerization. So someone is also asking, what about the ozonolysis? So ozonolysis, we shall also be able to look at it, but of course not today, but we can try it out, ozonolysis. Though on our coverage, these are the major reactions that we are supposed to cover. So what we're looking at are the major reactions that we are supposed to cover according to our coverage. Let's go direct to number 1, addition of hydrogen or catalytic hydrogenation. Let's use only 1 minute before so that I can remove this dot which was put on our screen. Just a minute, and then I bring it back. Yeah, very good. I think it has gone off. We can be able to see what we have on the screen very well. So number 1, we are looking at addition of hydrogen, which we have also called hydrogenation, and there is the one catalytic hydrogenation. I want only one person to tell us what you know about hydrogenation. Then we shall write the equations and then we move on. Let me start with Mapel Joseph. Joseph, unmute. I like the way we are participating. Good afternoon. I like the way we are participating and very active. Yes, Joseph. Yes, Joseph.
Hydrogenation of alkenes. Master.
Yes, please.
I'm saying hydrogenation of alkenes. If we had alkenes, we end up getting what we call alkenes, and this is in the presence of
It is done in the presence of?
Alkenes. It is done in the presence of catalyst at a temperature of 140 to 150 degrees Celsius, or it is done using palladium or platinum at room temperature.
Oh,
That
very
is what
good.
I know about hydrogenation of alkenes.
Thank you very much. Thank you. Thank you. You can mute. You can mute. Okay. Thank you. I think Joseph has managed to explain for us very well what hydrogenation is of alkenes. He has told us that in hydrogenation of alkenes, the alkenes are reacting with hydrogen in the presence. Now, he's telling us in presence of catalyst. And this catalyst has given us number one, palladium. Catalyst, he has also given us platinum catalyst, and has told us that platinum catalyst and palladium, they work at room temperature. And then he also talked about the nickel catalyst, and he told us that for it, it works at 150 degrees Celsius. And he has told us that when all this happens, they move from alkenes to form alkenes. We can clap hands for Joseph. He has given us a detailed description of what hydrogenation is. We are going to use an example. Let's have an example. And we are going to use, okay, which example can we use? Ruth, you have, your hand is up. Yes, Ruth. Ruth?
Excuse me. No, I was just adding on. Okay, I'm also going to give the example, but as adding on what I know about hydrogenation,
Okay.
that each bond, each double bond goes with a mole of hydrogen gas. So if I have an alkene with one double bond, it goes with one mole of hydrogen gas. But if I have an example, okay, that one is the example I'm going to start with is a bit complicated, but buta 1,3-diene will take 2 moles of hydrogen.
Oh,
the first example I can give is propene.
Propene, okay. Let's have that. So when you have propene, let me hope that is the formula for propene. Is it the one?
Yes, it is.
We are adding what?
We are adding hydrogen.
Hydrogen in presence of what?
Of nickel catalyst.
Of nickel catalyst. So
in temperature of 150.
50 degrees Celsius. What do we get?
We get propane.
We get propane. So propane. Is that the formula?
Yes.
Yeah. So we're moving from a propene, which is an alkene, and we're getting propane, which is an alkane. I believe that is it. Can you tell us the mechanism? Can you take us through the mechanism of how this one comes about? Ruth?
The mechanism.
Okay. Yes.
Let me see. The mechanism. I hope I don't mess up. So no, let's pick another person.
Okay, thank you. That was good. Now we can have another person. Samuel. Yes, Samuel.
I'm not very sure.
Okay, Samuel. Okay, Sisi.
Yes, teacher.
Yes, can you take us through the mechanism just briefly?
Okay, so I'm going to should I call it spreading the hydrogen bond?
Oh, So you're telling us,
then
okay, one thing, maybe what you're telling us that if we have our hydrogen here, this hydrogen, it has two atoms which are bonded by a single bond. Are we there?
Yeah.
So what are you
Yes.
telling us about these two hydrogens?
So those two hydrogens are both like, okay, I'm going to pick one. That one will have to go with one of the bonds.
But there is one.
On the propene.
It is partially what? One is partial
positive,
and then the other one is partial negative, yeah?
Negative. Yes.
Okay, now
then the partial positive hydrogen atom will go with one of the bonds in the propene.
In the propene. Okay, thank you. So which means you keep your microphone on. We have, you recall this is an alkene with a double bond, and one is a sigma bond and the other one is a pi bond. Now the pi bond, we say it is weak, and therefore it can easily be attacked. It attaches because it is weak. It can easily break. So which means what happens, because it is having electrons and it is weak, can easily break. It will break and it comes for this one, which is partially positive, and it will then you have this one, which is partially negative. And when it comes for this partial positive, this bond also will break and takes off this one, which is partially negative. Are we together there?
Yes.
Sissy, is it what you know? That is the one you are telling us?
Yes, sir.
Okay, good. So which means at the end of it all, we are going to have CH3CH. Now the other bond has broken, and therefore we have remained with a single bond. Yes, Sissy? So where is this hydrogen going to attach?
So that one will have to attach to the carbon that has the highest number of hydrogen atoms.
With more hydrogen atoms. So it means it will go this other side, it gets CH3.
Yes.
So what will happen? What will happen?
So this carbon that has one hydrogen will have to gain the hydrogen this side that gained the other bond, becoming a full electron.
Okay, but before that, is it because this one has this hydrogen is attaching to this carbon atom? Are you seeing that this carbon is going to remain unstable because it is now attached to only 3 bonds? Are you seeing that? So which means it is lacking, and therefore we put a positive charge. And then plus hydrogen ion. This hydrogen is the other one, this one here. This one which has broken. Are we there?
Yes.
Then at the end of it all, we are going to have this hydrogen come, because it is electron rich, it is going to come and make this carbon atom stable. And then at the end of it all, we shall be having CH3CH. Now this hydrogen is going to come attached to this carbon atom. They become 2 hydrogen atoms, and then CH3. And then we have our mechanism done. Thank you, Sissy, for leading us in that. Unless we have anyone with a question.
I'm also asking. So isn't it okay? Is it option to bring back the hydrogen, like the hydrogen and the nickel catalyst?
I've not heard very well. Is it what?
Is it optional for me to show what I've used, like the hydrogen that we use that first and the nickel catalyst?
You recall here, we have just used the hydrogen, 1 mole of hydrogen and nickel catalyst. The nickel is a catalyst. It has not participated in the reaction. It is just helping to speed up the reaction.
The labeling, like the way we've labeled here.
Do I also label that arrow in the mechanism?
Which arrow here? Oh, I'm not understood there. Like here,
Like here.
okay, I understand.
Yes.
Are you saying that here, putting now hydrogen, here, putting the hydrogen like that?
Yes. Is it
No.
optional?
It is not necessary. Why? Because up there, you recall up here, you have already written your equation. Are you seeing? You already have your equation, and you have shown that you have used the hydrogen in presence of nickel catalyst. So there's no need when you come down here on mechanism, the need of showing us that now here you have used the nickel. No. Okay. It is not necessary because it is a continuation from what you had up there.
Okay, thank you.
Welcome, Sarah.
Sir, please pardon some of us.
Sarah, you remain on now. Because today I want us to understand mechanism and we don't have issues again with mechanism. Sarah, are you there?
Okay, yes.
Okay, so we are going to repeat but using another example. So let's use part B. Which example can we use? Tell me, which alkene do you want us to use?
Butene.
Butene. But 1 in, but 2 in.
But 2 in.
But 2 in. So which means we shall be having CH3, CH, double bond, CH, CH, CH3. Is it true?
Yes.
We are using hydrogen in presence of what?
Palladium.
Palladium. Which condition do we use? Which temperature? Here it is room temperature. But you don't forget that we have talked about this here, that for palladium and platinum, they use room temperature, while for nickel, it is at 150 degrees Celsius. Have you seen?
Yes.
So the first example was for nickel catalyst, and now we are using palladium as our catalyst. So what becomes our product? What is our product now? What is our product? Let's be, yes? This is but 2 in. What becomes our product? Jovi, are you still there? Okay, Jovia has gone. Nyombi, let me move with Nyombi now. Nyombi Imla.
Yes, sir.
Can we move together?
Okay, sir.
So what is our product there?
The product is butane.
Butane. So it is CH3, CH2, CH2, and then CH3. And then this one becomes our butane. Now, what we want to show how we have come up with this product, and that's what we call the mechanism. Yeah. So what is our first step? I want us to move very fast. We have 1 hour, and with this 1 hour should be enough to finish these reactions. So I want us to move faster.
Now, the hydrogen dissociates to form partial charges. That is the hydrogen partial positive and the hydrogen partial negative.
Okay, very good. Okay, now which means we are having our hydrogen, which is dissociating to form the hydrogen partial positive and then partial negative. Okay, which means I bring our butane, but2 in, like that.
Yes.
What will happen initially?
We bring the hydrogen, which is partially positive, and it is going to be added onto. Being that it's an electrophile, it will withdraw electrons from the source of electrons there, that is the double bond, and take out, withdraws electrons, and it will be added.
So this one is also going to break.
and that one breaks off.
Oh, my space is not enough. How can I do it? So if I show that it's breaking like this, will it be very clear for us? Or I rub off. Maybe I rub off. Let me rub off this, and then we can repeat it. So we're having hydrogen, partial positive, and then we have hydrogen, which is partial negative. So the double bond is going to come for this one, which is partially negative, and then this bond will also break. Is it?
Yes.
Let's move faster now. So what do we form here?
We form CH3.
We form CH. Is it a full
CH3.
halo or a double halo? So we have CH3,
CH2.
So this hydrogen is going to attach to this carbon atom. So
yes.
Form a 2, and then you still have a single bond now, CH.
Then a CH, that is a carbocation.
Oh, carbocation. So there is a positive charge here.
Yes.
Then
and then
plus
our negative
hydrogen.
Nucleophile.
Okay. So what next?
Then that nucleophile is going to be bonded onto the other carbocation.
So it will come and then bonds to this carbocation. And then finally, we shall be having our product as CH3, CH2, CH2, CH3. And that marks the end. Thank you very much.
Excuse me, sir. I'm inquiring about the other first example. And my question is, do we always have to, do we follow the anti-Markovnikov's rule whereby the electrophile is added onto the carbon atom that has the higher number of atoms? Or
now, in hydrogenation, that one may not matter a lot, because at the end of it all, you recall it is hydrogen and hydrogen. Are you seeing that?
Yes.
But where we have a hydrogen and another atom, then Markovnikov's rule is going to apply. But now, what will be my advice? My advice would be, let us always follow that. So that the one who has is added another. You recall the Bible, it says that for those who have something, will be added. So that is Markovnikov's rule. Unless you have a peroxide. If you have a peroxide, that's why we go for anti-Markovnikov's.
Okay, sir. Thank you, sir.
Yes. Okay. You're welcome. Joseph, you can mute. We'll hear from Joseph. Joseph, you have a question?
Yes, Master, I have a question.
Yes, please.
So, I was asking,
do
you when you are dealing with hydrogen?
The problem, your network, Joseph. Joseph, what are you saying?
I'm saying.
Joseph, is it okay you put that question in the chat? You put that question in the chat. Okay, Vine, you unmute. Vine?
Yes.
Vine, unmute.
So my question is the movement of the arrows.
Tell me.
For example, this side where the hydrogen ion is.
Yes.
Is it supposed to come from the negative sign to the carbon, or is supposed to come from the atom itself?
Okay. So is it supposed to come from the negative sign or from the atom itself? So whether we put on the atom or from this, what we are looking at is this one is a nucleophile. It is electron rich, is going for electron deficient. Yeah. So whether it is coming from up here or on the atom itself, there's no big issue there. So long as we are showing the arrow, where the arrow is coming from and where it is going. You recall it was our NB here where we said that the reaction mechanism, arrows should move from a nucleophile electron rich, to electrophile which is electron deficient. Are we clear there? Okay. I believe now we can go to something else. Let's go to something else. Dr. Jimmy, if you have something, kindly let's see. Dr. Jimmy, any question? Unmute. Okay, Pauline, do you have a question? Pauline.
Yes.
Yes, where?
Like if it was a buta 1,2-diene, how could you do it?
Now, if it is buta 1,2-diene, meaning the number of molecules are going to change. Okay, that's like this. You're saying buta. This is 2, double bond, CH, CH. Now, if it is butane, which means the number of, please, you're in a noisy press. You're in a noisy press. You're in a noisy press. Okay, Pauline, you are in a noisy press, but I believe when it is buta 1,2-diene, meaning there are 2 double bonds. Someone talked about it at the beginning of this session when I'm looking at chemical properties, and we say that each double bond, it takes 1 mole of hydrogen. Now, since there are 2 double bonds, meaning we are going to need 2 hydrogen atoms, maybe in presence of nickel catalyst at 150 degrees Celsius. There will be 2 moles of hydrogen, because 1 mole of hydrogen will be taken by 1 bond here, then the other one will be taken by this one. I believe we are good to go. Martha, if you have a question, and then we can move on. Martha. Martha, unmute. Angel Maria.
Teacher,
Yes, please.
I want to know why is it a reversible reaction as we're heading to the second step during the mechanism?
Oh, so you'll find that most of the time you'll find that in the reaction that we are carrying out, there's where we're having a reversible, and then there's where we're having a full allo, especially when you're coming to the final product. So when we show that it is a reversible, meaning that the one we have formed, it can easily go back to where we are coming from. It is reversible. Like when you add the other one, it can easily go back. Then there is where we go to the final product. That's when we normally use a full allo. But those double allos, they are meaning that it is reversible. That intermediate product we have formed, it can still go back. Is it clear? Yes?
Sorry to interrupt, but does it mean that we have to cram the compounds, the alkenes that are reversible, that have an intermediate, that can go back to the alkene?
Oh, no, you don't need to cram. You look at this intermediate part here. Are you seeing it? So here, the bond has broken to remove the hydrogen, which is electrophile here, and then the other one is breaking down. There is a breaking to form this ion here. So when you come on this one, you see that when you get this plus the other, like when at this point we can have this one coming back to the other initial initial compound that we have. That is, if this hydrogen is removed, the one we have added. So when we put intermediate, those intermediate compounds we are having in there, we use the double allos. Even when we move on, we are going to see that there are some areas where we shall keep on using the double allos, but when you come to the final product, we should find that we are using a full allo, but for intermediate, meaning that the other compound can easily go back to the initial product. Because that is the
So
reason
does that
why...
mean from maybe a compounds of 4 carbon atoms and above, we expect to have them a bit reversible in their intermediate state, and then probably from propene downwards?
No, you see, even the one for propene, at first not yet, but we collected it.
Okay,
have you seen?
I've seen it.
Yeah,
yes,
we collected it. Yeah,
that means all of them are at the intermediate state, they can reverse back. Okay, thank you.
That's the one. Okay, now let's move very fast. I see time is running and we may not finish. Halogenation, addition of halogen, and now we are talking about in presence of inert solvent. Which inert solvent we normally use? Are you still there? Okay, let me have one person I can move with. Who is ready?
Yes, teacher.
Okay, Ruth.
Yes.
Ruth, are you ready? Let's move together.
Yes.
Do you know something about addition of halogen in the presence of inert solvent?
Yes.
Give me an example.
Okay, so when alkenes of room temperature are treated with halogens, that is chlorine or bromine in an inert solvent. Inert solvent is, for example, carbon tetrachloride.
Okay, I'm going to put an example. So we are saying, which halogen can we use?
We're using, let's use chlorine.
In presence of inert solvent, we said carbon tetrachloride. Okay.
The halogen rapidly adds across the double bond to give corresponding the double bond.
To give a corresponding what?
A corresponding vicinal dihalide.
Very good. That is nice. So, which means the chlorine atoms are going to attach themselves to this across the double bond. So this carbon atom takes one chlorine atom and the other takes another chlorine atom. That is nice. Now, without wasting much time, can you take us through the mechanism?
Okay. So, polarizes hydrogen. Okay, that inert solvent polarizes the halogen. So we have it dissociate. Let's use dissociate to partial negative and partial positive. So chlorine.
So chlorine is okay. Let me rewrite this. Propene, and they're saying that chlorine is partial positive, and then you have
partial negative.
Okay, so what happens?
Then, one bond, which is the pi bond, dissociates or breaks and goes to the chlorine atom, the chlorine. Then we have the another arrow.
This one will also disappear.
Yes, that one will disappear.
Okay.
Then we now have our alkene again, but with this other chlorine that was positively charged attached to it.
Okay, so where is this
carbon atoms?
This chlorine atom is going to attach to which carbon atom?
To carbon atom 2.
Which one?
The second one. Carbon atom 2.
This one?
Yes.
So you're saying we put it here?
Yes.
Then what will happen to this carbon
Then
atom?
that one, it acquires a positive charge.
Positive charge. Then also
So
we have
then
this one each block,
we add
which means we will have the
chlorine
negative there.
ion.
Okay.
Yes. Then we finally move. Okay, I saw you do it in the previous, and I don't have it here. But you carried this. Okay, let's try. Let me use the method I know. The next arrow.
The next arrow here.
Right under and under.
Like this?
Straight vertical. Yes. It gives you. We're going to have a vicinal dihalide. So we'll have that chlorine, the chloride ion attached to where we saw that where the carbon atom is positively charged.
Here.
There. Yes.
No, so what is causing this one to come here? So you're telling us that this one plus this one, it gives us this product. Without we don't need to show the arrow.
Okay, so for us we do not show it, but okay, let's indicate the arrow. From the chloride ion to yes.
It's all right. That is nice. Anyone with a question? And I believe since we know this, and what if someone at the first point, what if this chlorine was put on this first carbon atom? Ruth?
Yes, teacher.
What
if that chlorine was put on the first carbon atom, then for the case of propene, then the positive charge would be on the second carbon atom. So we'll have, I'm thinking, I'm not saying the right thing. We'll have the chlorine atom, the first one, which came from the partial positive charge, attached to that first carbon atom. Then at our last point, we'll have the last chlorine that forms the vicinal dihalide forming on the middle chlorine atom.
Meaning we could be having something like this, plus chlorine ion, and then finally we'll still come back here.
Yes.
And what is causing it to come there is this one, which is going to come and attach on that. Yeah?
Yes.
Yeah, so here we are just looking at an alternative. Someone is using this dilection, and then the other one has used this other dilection. So for this one, we may not have any issue because we are adding chlorine atoms. It's the same case we had even on hydrogen, addition of hydrogen. But we shall see where it matters a lot, especially when we come to those ones which involve like hydrogen atom and any other atom.
The mechanical.
Where that one is going to be applying. There are those people who had issues with mechanisms. Are we seeing that now things are becoming much easier? Let me know in the comment section whether we are now becoming much better or we still have some issues with mechanism. Today, I want us, by the time we finish this, let it be one of the way or one area that we enjoy if they talk about mechanism. Mugisha Henry, what are you saying? Mugisha Henry? Mugisha Henry?
Yes, sir.
Yes, please.
Is it compulsory that the inert solvent should be carbon tetrachloride?
It's not compulsory, but if we have another, that is the common inert solvent that is used, yeah? But if we have another inert solvent, we may apply it. But the question is, what if you use the one the examiner doesn't know? Are you saying that? So it's better we use the one which is common to each and every one. So carbon tetrachloride is one of the common inert solvents that are commonly used. That's why even us today we said, let's use that one because it is the common one. Yeah?
Okay, I get you, sir.
Now remain on the call, and then you take us through addition of halogen in presence of water. We are still on halogenation, but now this time round is in presence of water. Okay, tell us.
So they are in presence of water, I think, but I'm not sure.
So, and I want us to use this one, butene, but1-ene. We are having, maybe now we can use bromine. Can we use bromine or chlorine? Okay,
bromine.
let's first use chlorine. Chlorine in presence of water. The other side, it was in presence of carbon tetrachloride, which is a nat solvent. Now, this time round is chlorine. What is the product first?
Then the product is
what is the product? Hey, what is happening?
It's 1,2.
Okay, maybe tell me. CH3, CH2, CH. What attaches here? CH2, what attaches here?
On the first chlorine, in the first carbon atom, that one, there will be chlorine.
Chlorine. Then on the second here?
OH.
OH. Which name is given to this compound?
1-chloro.
1-chloro.
2.
2.
It's butol.
Yes?
Butol.
2-butol.
Yeah.
Or we could say maybe 1, 2, 3, 4. Since the because this is an alcohol, yeah? Because this is an alcohol and is on carbon 2, then you can say butane, maybe butane 2 on. Yeah? Yes, butane 2 on. This is B. Let me hope it is clear for everyone. Thank you very much. Now we run to mechanism. Do you think you can take us through mechanism, or we call someone else?
I can try.
Okay, let's begin.
So there will be reaction. Chlorine, we are going to react with water.
Okay. So chlorine is going to chlorine
to react.
Aqueous reacting with water. What will it form? Getting what?
Hydrogen chloride.
Hydrogen chloride. Plus.
Again.
This one?
Water. Really? Yeah.
Yes?
I think that's, yeah.
Okay, so you need to know the name. Hydrogen chloride. And then, so what will be the next step?
So we are going to get that butene.
Butene.
We add it. We dissociate chlorine. Yeah, so we get the hydrogen chloride.
This one?
Yeah, we dissociate it.
When you dissociate hydrogen chloride, what do we form?
We get hydrogen proton and
do you think, are we going to dissociate the hydrogen chloride? You recall our product. Our product is having OH. It is also having the CM. So if we go for HCl, it is going to become a challenge. Instead, now we can come to dissociating this one for this one for HOCl. But now, when they become polarized, what happens? Which one becomes partially positive and which one becomes partially negative between OH and Cl?
OH becomes partially positive and then Cl becomes partially negative.
Partially negative and then partially positive. And then what will happen? So you're saying that OH, then Cl, this one becomes partial positive, and then this one becomes partial negative.
So those double bonds will give electrons to OH.
Okay, then this one will break.
Yes.
Then what will be formed?
Are going to form CH3, CH2, CH, CH2, then OH.
Then OH. But you call your product you have.
So maybe if we don't,
Yes.
Maybe if we don't follow the Markovnikov rule,
because
we are going to put OH.
Which means your OH will put it here, and then here becomes a cation.
And
then we shall have Cl. Okay. And then finally, we shall be having CH3, CH2, CH, OH, and then we have CH2. Now this one is going to come and attach it to that carbon atom, and therefore we shall be having Cl. So that was your first method. But also we can use the second method, this one, where we don't need to first react. Now we have CH3, CH, 2, CH, double bond, CH2. So you have bromine and water. So since we have bromine, is it bromine or chlorine? We have chlorine, yeah?
Chlorine.
We are using chlorine. So the chlorine when dissociates, becomes partial negative and also have partial positive. So what happens? This double bond will come and comes for this partial positive electrophile, and then this one will also break, and then here we have our intermediate here, CH3, CH2, we have CH single bond, CH2, and then we have Cl. And then this carbon atom becomes a carbocation. And then we have plus Cl. But now you recall in the solution, we have a nucleophile of water. And you recall that this water molecule has this lone pair of electrons. These lone pair of electrons are the ones which will come and now attack. Because you recall, the allos always move from the nucleophile to electrophile. So when that one comes, still this one now will be a partial allo. So this will be CH3, CH2, this will be CH. Then here we have OH2. But now oxygen is having more oxygen atoms. Are you seeing that? It's having oxygen atom. Therefore, here we have it will be positively charged also. And then you have CH2, then you have Cl. So for us to make it stable, we can say we remove a hydrogen ion. But remove it, so it becomes stable now with CH2, CH, and then here you have OH. Here we have CH2, and then you have C here. Is it clear?
I get you.
Thank you very much for reading us in the first method, and now we have gone through the second method. If there's any question, someone can ask, but if not, then we can move on. Please, if you don't have a question, let's put down. There's Ashanti. Okay, Ashanti is put down. Sebaiya. Yes, Sebaiya. Yes, please. Yes, please.
Does the arrow attach exactly to the atom example? Yes, teacher.
Does the arrow attach? Now, are you meaning like here when the arrow is coming from the double bond coming to this?
Yes, teacher.
Oh, now, maybe let me rub off this. Okay, so the arrow is coming from the double bond, yeah? Then it is coming to this. It can be very close, even if it doesn't touch, but it can be very close, like that. But not putting it very far. You have seen some people, some learners, you find they are now doing it in this manner. They do, and then they reach it there. Now that one, when I'm marking, I will not mark that. So let it be closer, let it come closer to that atom where it is going. Where is it coming from? Let it be very clear. So it is very good for us to be very clear when we are showing where the arrows are going and where it is ending. So here, you will reach it there, and it is not touching there, but it's very close. If you're not very keen, you may think it has touched, yet it has not touched there. So it will be very close, and such someone who is squaring you is able to see the arrow very well.
Oh, thank you, teacher.
Now remain on the call, and then we go to what people have been asking. The hydrohalogenation. Now, hydrohalogenation is the one we call the addition of hydrogen halides. The one I also called at the beginning, the halogenic acids. So these are the halogenic acids, the hydrogen chloride, the hydrogen bromide, the hydrogen iodide. And we are saying that it is addition of these hydrogen halides across the double bond. Now, in this case, where we are having a hydrogen atom and another atom, we are saying the Markovnikov's rule applies. What are we talking about when we say Markovnikov's rule? So Markovnikov's rule says that the hydrogen attaches to the carbon with more hydrogen atoms. For example, if you look at this example here, it is a propene. This is propene. It has a double bond. We have this carbon atom and this carbon atom. We can see that this hydrogen on the halogenic acid, the hydrogen bromide, when it was attached, at first it was attached to this carbon atom with two hydrogen atoms compared to this one. So we see that they became 3. And then bromide, it came on this second carbon atom. So, which formed two bromo propane. So that is the one that we are having. And now we say that also, if we don't use Markovnikov's, there is what you call anti-Markovnikov's, not anti, but anti-Markovnikov's. The anti-Markovnikov's, this one works if there is a presence of a peroxide. When the peroxide is present, like an organic peroxide, sometimes we can always label it with this. where this can be an alkyl group and this another alkyl group. But if there's presence of any peroxide, then we use what you call anti-Markovnikovs. Now, when you say anti-Markovnikovs, is now the opposite of the Markovnikovs rule, meaning now the hydrogen will attach where there are less hydrogen atoms. We are going to do some practice items as we go through this. But as I said, this is the one we're calling the hydrohalogenation, or what you call addition of halogenic acids or addition of hydrogen halides. Azendi, you have a question. Let me have Azendi. Azendi, unmute. Azendi? Audrey? Audrey?
Good evening.
Yes, Master.
Now, let me have one person start, then the other one will follow.
Azendi if I start.
Okay. Who is starting? Azendi, are you there? Azendi? Okay. Audrey, take us through. Audrey, unmute.
Saying good evening, teacher.
Good evening, how are you?
Fine, thank you. So as inquiring to note that if the anti-Markovnikov, like, is anti the reversal of Markovnikov, since
Yes.
like Markovnikov deals with like attachment to the ones with the more hydrogen atoms. So that means anti-Markovnikov, we are attaching, let's say, our
hydrogen,
the neutrophile that is negative, partially negative, will be attacking the ones with the carbon atom with the less hydrogens.
Yes. So the hydrogen, when it is anti-Markovnikovs, the hydrogen now attaches the carbon with low hydrogen or less hydrogen atoms. So it is the opposite of the Markovnikovs rule. And we're going to have an example. We're going to have two examples. The one which is clarifying on Markovnikovs and the one clarifying on anti-Markovnikovs. Now, if you're still there, I want you to...
Teacher, I'm still inquiring on a little something. You know our previous examples where we had like but2-ene and everything.
Yes.
We were also attacking the ones with the more hydrogen atoms. So are we still following what Markovnikov's rule, or Markovnikov is followed in specific in examples, if I should say?
Now, Markovnikov's rule, you'll find out that we're applying it in the examples or in the reactions which involve hydrogen ion. Maybe it can be hydrogen with another atom. Maybe it can be hydrogen and water. It can be hydrogen. Like when you see the rule, the way it states, it is specifically talking about a hydrogen. Maybe let me state for you. It states that when a molecule containing, you listen, when a molecule containing a hydrogen atom is added to an unsymmetrical alkene on a carbon atom carrying the functional group. Are you seeing that? So, and Markovnikov's rule applies if we're adding a substance which consists of a hydrogen atom. Now, for the previous one, like the one we are having for halogenation, we are adding only chlorine atom or bromine atoms. Those are not hydrogen atoms. In those compounds you're adding, there's nothing like hydrogen. So anti-Markovnikovs may not work. Markovnikovs may not work. But as I said, for us not to have very many things in our mind, let us use that one. If we're also adding like chlorine, and we're adding it to maybe this compound here, we can use that. The one which is having more, we give it first. The one which is having less, it comes later. You get? So so that we don't always confuse ourselves in one or the other, that have I applied Markovnikov's or I have not. So that's why I was trying to tell someone who asked that let us have that one. But for Markovnikov's rule applies if we're adding a molecule which has a hydrogen atom. And it normally applies if the compound we are working on is unsymmetrical. Do you understand when we say unsymmetrical?
Teacher, I can talk more about it.
Yeah, unsymmetrical, you recall when you talk about symmetry, lines of symmetry. If you talk about lines of symmetry, like for this triangle, which is having two sides which are equal, how many lines of symmetry can we have? Are you seeing this line of symmetry?
Yes.
So what does it mean? This, it is going to have, this side is equal to the other side. Are you seeing that? So when you say symmetrical, and unsymmetrical. So when you say symmetrical, for example, butene, we can have but2 and but1. So but2 becomes symmetrical. You look at this. Where the double bond is, what is on the other side is the same as what is on this side. So we say this one is symmetrical. But when you come to but1, it is CH3, CH2, CH, double bond, CH2. Now this one you say it is unsymmetrical because when you look at what is here, it's not the same as what is on the other side. Have you understood that?
Yes.
So we say that for Markovnikov's works on symmetrical alkenes, while for these ones which are symmetrical, you recall this carbon atom and this carbon atom, they have the same number of hydrogen atoms. So when you are adding, it can add on any side it wants. Are you saying why it does not apply on symmetrical? Have you made some analysis on that now?
Yes, but teacher, you said Markovnikov's applies on those with symmetrical.
No, it applies on those which are unsymmetrical.
Oh, okay. Now understood, even with the definition of Markovnikov's, because it will be attached with the one with the H2 instead of our.
Yes, very good. But now the one which is symmetrical, they are the same, so there's no carbon atom with more hydrogen atoms. Have you seen?
Yes.
Time is not our friend. I would like us to move a little bit faster. So let's have an example, and we are going to apply Markovnikov's. Can we move together? Because of time, we move very fast. Audrey, are you still there?
Yes, teacher.
Which example can we use? Let's be faster.
The other one of but2 in, CH3.
Okay, let me first give you mine. Give me the name of this. Give me the name of this compound. What is the name of this compound? Get for me the name. And then after that, you tell me the product it forms. Okay, before you put the product, before we name it, can you give me the product? Just read for me. Let's be fast because of time. Hey, where are you? Audrey? Okay. Audrey seems to have disappeared. Audrey, are you still there?